And we talked about the remainder theorem yesterday. And remember how I told you if you want to see if you've got the right remainder, plug in the root, and if you get 17, then 17 should be the remainder, okay? So that's what we're doing today, and it kind of boggled my mind when I first learned the remainder theorem. Like, how did someone realize this? How did they come to realize that that was the situation? So I kind of thought about it, and my best guess is that when we do long division and we get a remainder of 0, we do know that getting a remainder of 0 tells us that this was a perfect factor, yes? And if it's a perfect factor, then 3 is a perfect root, yes? So we have this. So since it was no remainder, it is a factor, and therefore 3 is a root. Now visually, what does it mean to be a root? If 3 is a root, we know the graph goes through this point somehow, right? I don't know what it does, but it goes through, right? And the coordinates of that are 3, that's your root, comma, 0. We all agree that's the point 30 if it's a root, and the remainder was 0. Does that make sense? So then when somebody goes, so I kind of write this, f of 3 equals 0, when something is a root, okay, it's an x-intercept, so this is the point 30, and therefore your remainder kind of shows up as the y-coordinate that goes along with that x-coordinate. So the example we looked at yesterday was this. X plus 5 after long division had a remainder. So it's not a factor, and it's not a root. It's not negative 5 comma 0, because it's not a root. It's negative 5 comma 6. And so we learned that the remainder you get is actually the y-coordinate that pairs along with the x-coordinate. What was the potential root? We found out it was not a root, but if it had been, negative 5 would have been the potential root. And I only say potential because it did not actually give us a remainder of 0, so therefore it was not actually a root. It's just a random point on this graph. If you look at this graph, it contains that point. Kind of crazy, okay? But that, in a nutshell, is what the remainder theorem is, and we can use the remainder theorem many, many different ways. Number one is to check your long division. If you get a remainder of 17, you can plug in the root and see if you get 17, okay? So here we are to start our notes, the remainder theorem. If f of some number equals 0, okay, we know from a point perspective that means n comma 0. Then when the function is divided by x minus n, that's the factor. N equals the root. F minus n, or x minus n, is the factor. There will be no remainder. Okay? If when you plug a number in you get 0, aren't we accurate in saying if the y-coordinate is 0, we have an x-intercept at n, right? Y-coordinate of 0, x-intercept equals n. And if n is an x-intercept, then it is a root. If it is a root, then x minus n is a factor. And therefore we have no remainder. All of these ideas, and there's 3 or 4 of them wrapped up in there, are interconnected. They're all intertwined. The x-intercept, the root, the factor, the not having a remainder. Okay, that's when something is a perfect factor. So when we're asked this question, determine whether or not each of the following are factors, we don't have to do long division. You can. You definitely can. And you all know that if you do long division and you get a remainder of 0, then yes, it's a factor. But you don't have to do long division because we can use our remainder theorem to make it quicker. What could I plug in to see what the remainder is going to be? What'd you say? -2 or +2? Let's decide. Positive, right? Because if this is what we're checking to see as a factor, then we're checking to see if positive 2 is actually a root. So if you just check f of 2 up in our function, that'll be 2 cubed plus 2 squared minus 4 times 2 minus 4. I get that f of 2 equals 8 plus 4 is 12. 12 minus 8 is 4, minus 4 is 0. That would be my remainder if I had done long division. So is x minus 2 a factor if I get a remainder of 0? Yes. Much quicker, isn't it, than actually doing the long division? Nate? You would just say that's on your calculator. I would want you to show the plug-in and like what you plugged in, but then just crunch it down. That's okay. If it says algebraically, then that would, you got to show some more work. But he's right. Could you just plug that in on your calculator and see if 2 is a root? Yes. What we're trying to get you to like really grasp though is the remainder theorem. And you're using kind of the visual concept. You're not really using the remainder theorem. So this is why I'm doing these this way, is to kind of help that sink in. So for this one, I'm going to check f of what, Maddie? F of 3. 3 cubed plus 3 squared minus 4 times 3 minus 4. Bo already did it. What'd you get, Bo? 20. So if I had done long division, the remainder should be 20. That's where it's kind of a checking mechanism, too. The remainder should be 20. So is it a factor? No. But guess what? The point 320 is on that graph. That point is on that graph, just like the point 20 is on that graph. You with me? And what do we check, Micah, for C? F of -1. Go ahead and do that. What do we get? -6. So was it a factor? No. But -1, -6 is also a point on my graph. So here I just graphed this. And you'll be shown graphs of this and asked to use, you will be asked to use the remainder theorem. We'll get to one of those questions today. We'll go there. So I went from -20 to 20. So 320, well, I can do second trace value. And I can say, if an x is 3, what's the y coordinate? 20. And if x is -1, second trace value. If x is -1, there's my point. Oh, you lied to me. How come no one corrected her? I have to trust you kids. So it did equal 0. So there was no remainder. So yes, it's a factor. And hence we have the point -1, 0, which obviously on my graph you see is showing up, until it's better, showing up as a root. And so is 2, 0 showing up as a root. So the y coordinate is the remainder, which I find kind of interesting. The y coordinate that goes along with the point is the remainder. So again, to me, there's so many connections here for us to be made that I find it very difficult to know how to best teach this, because between the graphs and the long division and the point, it's all intertwined. So this is kind of the if-then sort of think proofs in geometry for a minute. If f of n is 0, then n is a root. And if n is a root, then x minus n is a factor. And if x minus n is a factor, then f of x divided by x minus n will have no remainder. And then it kind of, the cycle goes back to the beginning. If we have no remainder, then f of n will equal 0. You see kind of all of those ideas that are intertwined? I should kind of do that. If there is no remainder, then f of n is 0, and it kind of comes full circle. And actually, just thinking of it now, I could do kind of something similar to this if f of n did not equal 0. If f of n was just a number, let's kind of write this down. If f of n equals, or does not equal 0, then n is what? What would be the equivalent statement here? Then n is not a root, right? If f of n does not equal 0, then n is not a root. And if n is not a root, then x minus n is not a factor. And if x minus n is not a factor, then what? Division will have a remainder. And we'll just call it R. And if it has a remainder of R, if there is a remainder, not right now, I'm sorry. Wait till I get through this and then I'll let you go. If there is a remainder R, then f of n equals what? If the remainder is R, then what does f of n equal? R, which we assume is not equal to 0. So it comes full circle. There are 4 kind of interlinking ideas here. And then we could go back to the beginning because f of n equaled R, which was not 0. And we could kind of keep going through this domino effect of logic. Does that make sense? I'm going to update that. I like that. All right. Exercise 2 here. This is, well, I guess I can talk about this quickly. It's just kind of all symbols. But if you have a polynomial, p of x, and you're dividing it by a linear factor, you get q of x, which is the quotient, plus p of a, right? Your factor that you're dividing by is x minus a, so p of a is the remainder over x minus a. Okay? Take it or leave it with that notation, but there's so much going on here, they have to kind of give us it in generic symbols. So here we have a ratio. If it was placed in this form, which is the quotient plus the remainder over x minus 9, that's because we're dividing by x minus 9. If it was placed in that form, in other words, if we were to do the long division, where q of x is a linear function, so we get a linear answer, then which of the following is the value of r? We don't actually have to do long division to find out the remainder. We have to do f of what? 9. Very good, Maggie. Because the factor we're dividing by is x minus 9, so we just have to do f of 9, and here's our function. So that's going to be 9 squared minus 11 times 9 plus 22. We get 81 minus 99 plus 22, which is 4. Much easier than long division. Now, there are definitely cases where we have to do long division, like on last night's homework, unavoidable, if you're trying to factor or find all the solution. But if they're just interested in one specific potential factor or one specific potential root, there you go. Okay? Any questions so far? I want to look at this bottom example first because I don't want to have to rush through it. This was on a Regents. Testing the remainder theorem from a visual perspective. Take a minute to read that, and I want you to mentally choose your choice. What would you pick on a test? And I'll have you hold up your number on the count of 3 in a minute. I'm going to grab that tomorrow. These too many pink sodas. Happy to like them. Awesome. Some non-voters. Very good. It was number 1. Okay. When I first taught this, I didn't bring in the graph of it and understanding the point, the fact that 2 of 0 gives you a remainder of 0, but also that that's a point on the graph. So I'm trying to teach it a little bit differently, and I think that that kind of worked because you mostly got it right. If we're dividing by x minus 2, we're kind of checking f of 2. And if you look at f of 2, which is negative 1, negative 2, negative 3, negative 4, negative 5, that's the remainder we would have gotten. And hence that's the point on the graph. So option 1. So they phrased this so the people who didn't want to learn the remainder theorem, who decided, nah, I'll just do long division every time to see what the remainder is, they make it impossible here. Although I will say I did have kids do this. Tell me what I'm doing here. Raise your hand if you know what I'm doing and how kids can still get the answer, but it's a lot longer. Nathan? Yeah, I actually had kids write the equation of the parabola. So I used the vertex form because I saw my vertex was 1, negative 6, HK. Wrote it, I just plugged in my y-intercept, 0, negative 5 to solve for A, got an A of 1. So here's my equation of the parabola. They rewrite out the equation of the parabola to this, and then they did long division because they were so insistent on not using the remainder theorem. They took long division and divided by x minus 2 to see what the remainder was. Crazy. I don't think anybody, well, even if, that's the way I taught it, very few people would get that right because there's so much logic behind that, which is great that they thought that, but man, did they do way too much work, right? That wasn't the intention of the multiple choice problem. They wanted to see that you made the connection between the point on the graph and what the remainder would be if you divided by the factor. Do we make sense of that? Okay. And up at the top here we have, is x minus 3 a factor? The quick way is just to do p of 3. And then we'll get it equal to 0 or not 0, and that'll be our yes or no. Is x plus 5 a factor? We'll do p of negative 5. Part C and D are switched somehow. That's weird. A, B, C, D. For C, is x minus 5 a factor? We'll just do p of 5 in C. And in D, is x plus 1 a factor? We'll do p of negative 1, and we will see yes or no. Got it? Pretty straightforward. Exercise 5. Tricky Common Core way of asking. For what value of k will x minus 4 be a factor of this? See how the k is missing? We want x minus 4 to be a factor. So what number do we want to plug in for x? If we want this to be a factor, positive 4. We want to plug in 4, and what do we want it to give us? If we want it to be a factor, we want it to give us 0. So if I plug in 4, 4 squared plus k times 4 minus 52, I want that to give me 0. So that 4 is a root. And solve that. Pretty easy to solve that. Interesting, right? They love leaving out variables and asking you, what would that need to equal for such and such of a condition to happen? You saw it was discriminant. Do it again here. So what's the answer to that one? Add 52 over, subtract 16 over, divide by 4, come over k. What we get? 9? 16 plus 36, yep, 9. K equals 9. Conceptually, guys, that's kind of heavy stuff. I promise you I don't try to make it difficult. I'm just trying to make you see all these connections